Alright guys, so moving on, we will be working on our next assemblies project, and today we are going to be making an Ender-3 Hotend. So in the world of 3D printing, a lot of reasons why people run into a ton of issues and then just abandon it is because there's so many things that can go wrong. And very often, all of your errors are held in the heating element, where all of your plastic is being pushed in, melted, and then extruded out. And if you can understand what all of those components inside the Hotend does, then maybe it'll help you out in the future. So today we're going to be going through all of the components that make up the Hotend, what they do, how they interact with each other, so then when you guys run into any problems in the future, you know exactly what to do. So because the Ender-3 is such a popular 3D printer, you can actually go onto GitHub and find the actual full CAD model where it shows all the intricate details such as the motherboard, the LCD screen, the aluminum extrusion, all the wheels, which is great. But when you actually dive a little bit deeper into it, you'll find there's a ton of detail that's missing, especially in the Hotend and all the individual pieces that actually make up some of the most important parts of a 3D printer. So for this project, we are going to be making what's called an assembly using internal components. So instead of working on multiple individual files that then get collected in an assembly file, just like we did for the fire piston, all of our files' information is going to be held in a single page, a single tab. So if anything gets changed on one component that's connected to another one, there's some type of shared linking connection between the two. So for a lot of people, this becomes far easier to deal with assemblies, and like I said, is purely personal preference. So we're going to be starting off by changing our document settings from inches to millimeters. Everything that is in 3D printing is in metric. So everything is millimeters, kilograms, millimeters per second, Celsius, it goes on and on. So we may as well design this in a way that it deals with metric units a little bit easier. And you'll find things line up and all the numbers are a little bit easier to work with as well. We'll be starting with the nozzle at the very bottom and then building upwards to our PTFE tube. So we're going to start off by saving this file as a Ender-3 Hotend assembly. Because we are making an internal component assembly, we don't need to have a whole folder full of individual stuff. So you'll see that our top file has now changed names to update with that. With our top file already activated, we're going to be making a new component, and this one, instead of checking external, we're going to change it to internal. And this one is going to be a 0.4 millimeter nozzle. The 0.4 millimeter, that is the hole of the orifice of all your plastic is being extruded out from. And then you'll find that this already has a parent selected. That is just saying that this is our parent and all of our components are the children. They're the sub-components. So we can just click OK, and then we're going to start off by making a new sketch on the top plane. And this is going to be a polygon. We're going to be making a hexagon that starts from the origin, pulls outwards. We don't really need to, but we can just make this top line horizontal. And then we are going to be using our dimension tool to make this a 5.95 millimeter hexagon. There we go. Then we're going to be finishing this sketch, getting a three-dimensional view of our piece, hitting E for extrude, and then extruding this up 13 millimeters. Our next portion is going to be making our sketch to actually cut away all of the information. Mainly, we need to have that little angled tip at the very end of the nozzle. We need to have a flat section ground for our thread, and we need to have a hole that goes all the way through it. So to do this, we are going to actually be expanding this component and turning off our body, so then we can make a brand new sketch on the front plane. So using our line tool, we are going to be making the geometry that cuts out the very center. This is going to be a central axis that goes down, off at an angle, and then straight over to finish that off. We're also going to be making a little triangle down here that will cut in the very angled nozzle, and then we'll just add in a little rectangle over here that will then cut away to make our thread. The only constraints that we really need to add in is adding a collinear connection between the top of the rectangle and then the top of this line piece, and adding a coincident relationship between the bottom of the triangle and our origin. Now you can find all of the dimensions that we'll be putting into this sketch in our packet, but we'll just be going through and smashing all of these. For example, our little triangle down here, this is going to be 4 millimeters tall, and the very tip of this to the origin is going to be 0.75. So if you have any of this geometry that kind of overlaps or interferes with anything, remember you can always click and drag any of these blue lines, and it should kind of manipulate everything into the right location. So go ahead and check in your packet, and I'll meet you guys at the end of all these dimensions. All right, so all of our dimensions are in there. The one last thing I forgot to note is we also have a collinear relationship between the right-hand side of the rectangle and the right-hand side of the triangle. But that looks great, and now we have all of our sketches that are fully defined. We can tell that with the little red padlock over there. And we are going to be making a revolution cut to take this away from our little hexagonal stock. So we can just say finish sketch with there, click our revolution, select all three of these profiles, and then select the axis to be the left-hand side of this line. What you'll note is that this is also, there's a big warning, and that's because we have turned off our body, but we can turn that back on and you'll see that it does in fact cut everything through. Our operation is set to cut, so we can just click OK, and this is actually going to get us most of the way to the nozzle. Now, not only are we going to be putting an appearance onto all these to make them look a little bit more realistic, but we're also going to be kind of noting that the physical properties, the actual material physics of every single component is also really important as well. The heatsink made of aluminum is incredibly important. The fact that our heat break is made from steel that really doesn't translate heat as much is very important. Even more so, this nozzle is made from brass, which conducts heat very, very efficiently. So instead of adding in an appearance under our modify menu, we're actually going to be adding in a physical material. This one is going to be a brass. Unfortunately, though, we cannot just search it. So go ahead and go into metal and then scroll down until we see brass. There we go. So you can just click and drag this on just like we would our appearance. And now this also has the appearance of brass, but then all of the really important thermodynamic properties of the nozzle as well. This top cylinder right here, this is going to be taking a M6 thread, so we can go ahead and apply it to that face. We do want this to be modeled, and because we already made this to be 6 millimeters in diameter, this is already saying, yep, this is a 6 millimeter thread. So we can just click OK. So just like with all of our metalworking projects, anytime we have these sharp corners around, we want to add a chamfer just to get rid of that. But we actually have two sharp corners that I want to get rid of. That is the inlet to this hole up here, and then this sharp corner on the outside as well. And these are going to be set to 2 different dimensions. So let's go ahead and add a chamfer tool, and we're actually going to be using this box in the middle to add multiple dimensions of chamfers to different components. So I can just click this inner ring. This one is going to be 0.2 millimeters. If I was to click this bottom edge right there, it would also apply a 0.2 millimeter to it. I don't want to do that, so I'm going to click this plus right here, then click the outer section. I want to set this to a 0.1 millimeter. So now you can see I've got one edge at 0.2 and one edge at 0.1. There we go. Then we can click OK. Now, like we've done before, with all of our metalworking threads, we need to chamfer this top edge just a little bit. Having it be completely flat on the top will give us a really annoying challenge of screwing this into the mating thread and unscrewing it over and over again. It's just going to be kind of a pain. So to fix that, we're going to be making a new sketch on the front plane, and we're going to be clicking P for projection, and we're going to be clicking this outer line of our hexagon and the very top surface of our thread. Then we can use our line tool and make a little triangle, and this one is going to be having an equal constraint on the horizontal and the vertical line, and we can set this to be a 1 millimeter edge triangle. There we go. And then using our collinear relationship, we can line the right-hand side of the triangle with the right-hand side of the hexagon. And then again, using the exact same tool, we can use to apply a collinear relationship between the top of the triangle to the very top of our piece as well. And as you can imagine, we're going to be finishing this sketch and then adding a revolution cut about the axis. And this axis is going to be, well, it's going to be a little hard to click. So we can either zoom all the way out and select that, or you can just rotate your piece to the underside so you can kind of see through that hole on the bottom. But that's looking great, so we can just hit OK. Now the 0.4mm nozzle is just the most common diameter nozzle that you'll find in 3D printing. If you have to print a really large piece that just has to print really quickly, you can print it with a much larger nozzle so that it prints faster, but it doesn't have as much resolution. In a similar state, if you're printing a really highly detailed miniature, you can print it with a smaller diameter nozzle, and it'll take a longer amount of time, but you'll get a much better project at the very end of it. So to actually distinguish all of these, they usually print on the very front of it the diameter of the nozzle, and we're going to do the same thing. So we're going to make a brand new sketch on that front plane, and we are going to be adding some text to this. So I'm just going to be making a text box. Again, it doesn't have to be anything specific. They're just kind of lined up with these top corners of our piece. And we're going to type in there 0.4. Now the height of our piece, as you can see, is a little bit too big. So we're going to change that to 1.25 in height. And we are going to be aligning this to the center and then aligning it to the middle. And strangely enough, these are actually upside down as well. So we can set this to negative 180 degrees so it's in the right orientation. And then we can click OK. And then finish this sketch, because now we need to extrude not that actual surface, but the text itself. We're going to be going negative 0.1 millimeters and cutting into that surface. All right, so that is this component all done and dusted. So I'm just going to go ahead and save this whole file right now. And now we can go up to our top file and activate this. This is the really important step. Every time you make a new component in an internal assembly, you always have to activate this top bar. If you look at our assembly, you can see we've got a little white cube, which means components. And if you have our top file, which has multiple components together, it's going to look like all these cubes stacked on top of each other, which means this is an assembly file. So we'll be adding in a new component that is already internally checked, and we are going to be making a heater block. This is the big block of metal that the nozzle will then screw into, and it will have a set of holes that we can actually house our thermistor and our heating element at the same time. So now that our heater block is activated in the browser, we can now start to make our sketch and then build our bodies, which then will be attached to our lower components. This is where the internal components really shine, where if you change some feature about a component that's connected to other parts, then everything else will shuffle around to accommodate this. For example, if I make all of my components that stack on top of my nozzle, and then I change the height of my nozzle, all of my parts will then lower down to accommodate it, but they won't separate. So I'm going to go ahead and make a brand new sketch, not on any of these planes, but on the very top of my hexagonal face. And then I'm just going to click, well, I'm going to flip it around so it's in the right orientation with my view cube up there. And then we're going to be starting off with a very simple rectangle and then a couple circles on either side. And I'm going to be putting in all of my constraints and all of my dimensions that you guys can find in your packet. All right, great. So all of our sketches and all of our 3 circles and rectangle is all built in place. Now we can go ahead and click Finish Sketch. And we do want to extrude this profile upwards. And what you'll want to really take into account is that if you just click this profile, yes, it won't select the 3 circles we have, but it also won't select the little corners of our hexagon as well. So go ahead and spin your view around so you can select all 6 of these points. Then in the distance section, we want to extrude this upwards 10 millimeters. Now these holes that we have here and here, these are known as clearance holes, or sometimes known as through holes. Basically, we're going to be having a bolt that passes through this hole and attaches to our heatsink at the very end. And because we don't want any proud bolts to kind of be scratching around on a 3D printed part, these are going to be what's called countersink bolts, where they have a flat head and then an angle on the underside. So to accommodate that angle, we are going to be adding in a chamfer on the top of these two holes, and this is going to be set to 1.5 millimeters. The other feature that we want to put in there is a thread on that hole that we have that our nozzle can actually screw into. But as you can see, our nozzle is in the way. So I'm going to go to my browser and actually turn off that component, and that will allow me to put a mating M6 thread in there. So just go ahead and check that so it's modeled, and then click OK. So now you can see I can turn my nozzle back on, and it does in fact screw into it perfectly. And just like the nozzle, I also want to put in a physical material. This is going to be an aluminum, and I'm looking for 6061. 6061 aluminum is probably the most common type of aluminum that you'll find in machining. It's relatively soft, but still has some good amount of toughness. So it's easy to machine, but it'll give you perfectly reasonable real life projects out of it. So you can just add that on there. You can see it's changed color as well. Now I'm going to be putting in a new sketch on the right-hand side of the block. And in here, I'm going to be putting 3 circles, one on top of the other over here. So I can just add a horizontal constraint between these two. And this is going to be the housing for our heating element that will actually heat up our nozzle and allow us to melt the plastic. And then we also have one bolt over here that will actually hold in a thermistor just below it, which is basically an electronic thermometer, which will allow us to really accurately tell the computer just how hot our nozzle is and when we can turn off our heating element because it's already at the right temperature. Now with all of our sketch information put in place, I'm just going to go ahead and click Finish Sketch. And now I need to do three sets of extrusions because all of these profiles are actually going to be cut to different depths. So we can just extrude this top one. That's going to be -4 millimeters. As soon as you hit OK, all your sketch does kind of disappear a little bit. That's fine. We can always expand our sketches and turn back on sketch number 2. My bottom one is going to be -5 millimeters. And then this larger hole over here, I actually want it to be cut all the way through. So I could type in -20. The other thing that I could do is change my distance, or excuse me, and my extent type through all, and then flip the arrow so it does in fact cut all the way through. And then we can just click OK. We're also going to be putting in something known as a set screw or a grub screw that goes in right from the underside and just barely puts some pressure onto the heating element so it doesn't slide outwards. So to do that, I'm going to be starting a brand new sketch on the underside of this component, clicking C for circle, and I'm going to be making a 3 millimeter hole that is 4.5 millimeters down from the top and has a vertical constraint between the center of the circle and the origin. Then we can just finish that sketch. And because I want to extrude this through the block, I can just extrude this, but instead of actually putting in a dimension or saying through the entire thing, I can actually change my extent to object and then select this inside face. And now if there was any important information on the very top, it wouldn't interfere with it whatsoever. And this hole that we just made is going to be receiving an M3 thread. We already set it as 3 millimeters in diameter, so it goes, yeah, I kind of know what you're doing. So it's just going to automatically do that, and we do want to make sure it is a modeled thread, and we can click OK to that. We also want to add a similar thread to this top hole up there. So let's add another thread right there. Again, it is still an M3 modeled thread, and we can just click OK. Now, unfortunately, we have in fact run into a bit of an error, and that's because all 3 of our threaded holes actually don't have a chamfered entrance to this. So we have to kind of roll back the clock a little bit and mess with our timeline a little bit. So there's a few tips and tricks that we can do to kind of change this a little bit. First things first, if you take a look at our timeline, you can see one thread is actually way earlier than the rest of them. And because this thread doesn't interact or doesn't affect any of the other later on features, we can just click and drag this thread all the way to the front of them. Now we can roll back the clock and undo all of our threads. So now that none of our threads are in the way, we can now go ahead and add a chamfer, And we want to add it to not only the holes, but also all of the edges as well. So we can just select the 5 faces of the cube, all of them except for the underside. And this will add a chamfer to all of those faces at the same time and all the edges that intersect with them as well. And we also want to add a chamfer to our grub screw. But we do have our nozzle in the way. That's kind of annoying, so I'm just going to turn that off, and then to that hole as well. And we want to set these to a 0.25 millimeter, so pretty small. And then when we turn that back on and then go back to our timeline and add in all of our threads, they have now the appropriate ease of use to screw in any of the other components. And we can go ahead and turn our nozzle back on. So now this component is all done, so I'm just going to go up to my browser and click this little white dot just to the right of it, and this will now activate the top file, and it now enables me to work with all of the other components below it. That would be the nozzle and the heater block. And what you'll notice right away is now I have all of the timeline features associated with both parts. This gets really complicated really quickly because now it means our timeline, if we have a lot of features to it, which we will, is going to be gigantic. So I'm going to be compressing all these, making a group. So I can click the first and the very last of my timeline while holding down Shift, which highlights all of them in between. I can then right click it and say create group. So now I have this little plus sign, so I can click and expand this to show me all of the individual features that make that up. And I can also right click this and then rename this to say nozzle, for example. And I'm going to do this with all of the remaining components that we have as well. So I'm going to be clicking the first component, or the first feature, holding down Shift, clicking the last one, and then right clicking and saying create group. There we go. So now our timeline is much more compressed, and then any additional features that we have in there won't look so blown out. And just like we ran into the same issue with the fire piston, I can in fact click and move this around. And I really don't want to do that. So I'm going to go ahead and right click this nozzle in the browser, and I would like to ground it. So it means this is unmoving, but if I add a joint to any of the components that are connected to it, they also will not move. So because these two components are already in the correct orientation, I don't need to add in just a normal joint. I can add in an as-built joint, which is a simplified version of joint if everything's already in the right location. So I can just click as-built joint, select my two components, saying, yep, do you want rigid? Yep, yes we do, and then click OK. So now I have a joint between the two, and I really didn't have to take it apart, look around, click different faces, and hope they join up. It's just kind of done, which is much nicer. This is the appeal of the internal component assembly process. You'll also notice at the very bottom of my nozzle, I do have a little joint icon. And if that's kind of distracting to you, if you really don't want to see it, you can always go into your navigation bar and click your display settings, go down to object visibility, and then scroll down to joints and uncheck it. So our next component that we are going to be adding in is known as the heating element. This is the electrical component that when you apply current to it, it converts electrical energy to thermal energy, which actually allows us to melt the plastic in 3D printing. It's a very, very simple part. It's usually just a cylinder with a couple wires coming off of it, but the material is the interesting part. It can be made of different metals or usually ceramic, anything that can handle the intensely high temperatures. If you actually take the heating element out of the heater block, which pulls away a lot of the heat, and turn your printer on, it will actually start to glow red. It gets that hot, and so it needs to be kept inside this big housing that can pull away as much heat as possible. We're going to be making this very simply by starting a new component, and this one, like I said, is going to be called the heating element, and we can just click OK. Always double check that when you do that, your top file was activated. We're going to be making a new sketch on the right hand side, and this is going to be projecting that ring that we have, this little bore that we have in the middle. We're going to be using the circle tool, and this is going to be adding a 6mm circle. If you remember, we made this a 6.05mm hole. So it's just barely larger than our heating element, which means we've got lots of really fantastic surface area so we can pull away a lot of heat really quickly. We can finish this sketch and then extrude that profile all the way to the other side. If, in case you forget just how large it is, not a big deal, we can just change our extent type to the object and then select the other face of this. It'll say, yep, go all the way to there, and that would be 20 millimeters. Perfect. We can then hit OK. Now, just like with the other components, we are going to be adding in a physical material, and we're going to be looking for a ceramic. Ceramic, we can basically add any of these. Porcelain would probably be the closest, and it will add this kind of matte white finish to it. This is basically just a material that can withstand incredibly high temperatures. And then we are also going to be adding in a new sketch on that same right-hand face, and this is going to be 2 circles. There we go, and these are going to act as our 2 wires that are coming off the end. So by projecting the circle that we made initially, we can actually have access to that little circle. So by adding in a horizontal constraint to those circles, adding then some equal constraints to these 2, and then saying that these are 1 millimeter in diameter and they are both 1.5 millimeters from that center point, we can then define the sketch of our 2 wires. There we go. Then we can just say finish sketch and then extrude out these 2 circles 5 millimeters. There we go. And so that is our heating element basically done. When you're concerned about all of these different components that go into making it, you need to make sure that all of the manufacturable parts that you could potentially make have all the detail that you need and all the elements in there that are probably easier to just buy, like a thermistor or a heating element or PTFE tubes. Those can be generally roughly made, but all of our work and effort is going to be in the easily manufacturable parts. So with this component done, we can go ahead and reactivate our top file, and then we can add in our new component. This one is going to be a thermistor. Now, a thermistor is essentially just a very small glass bead that's got 2 wires running through it, and it's located inside this little 2 millimeter diameter hole that is right next to our heating element and right next to our nozzle. Simply put, this is a glass bead that has got 2 wires going through it, and as soon as it detects some sort of heat from a heat source, in our case the heating element, then it can detect very small changes in resistance, and the motherboard reads that as differences in temperatures. So this is a very simple part that is going to be located in this bottom hole right here with 2 wires coming off the other end as well. We're going to be starting off by adding an offset plane to this right-hand side of our heater block, and we want to be pulling it in 1 millimeter, or you can just type in -1 millimeters. Then we can click OK. Now we are going to be using the sphere tool that is under our create, and it basically just needs to know 2 bits of information. What is the radius of this sphere, and where is that point located? So we're going to be making a new sketch on that offset plane that we just made, and we can just type P to project the very center of this bottom hole. And as soon as we do that, we get a nice little point in the dead center. We can finish that sketch, go back into create, and make our sphere. And it's basically just asking us to select that plane, which would be our offset plane, select the origin of that, and then type in 2 millimeters for our diameter, and then click OK. To add on the other 2 wires, we're going to be making a new sketch again on that construction plane. So because we have made a component, that construction plane is actually locked inside the thermistor's component. So we can just go ahead and activate that again, make a new sketch on that plane. Again, we want to project that little ring, which will give us the very center of our circle. We can type C for circle and add 2 different circles on either side. These are going to be equally sized, and it may be a little hard to see what's going on, but we'll do it. And then by holding down Control, we're going to select the centers of the 2 circles and that little purple point in the middle and apply a horizontal constraint to it. These circles want to be 0.25 millimeters in diameter, so very, very small. And then they're going to be located 1 millimeter on either part, 0.5 millimeters from either side from the origin. There we are. Then we can just hit Finish Sketch. Now we can hit Extrude and select these two circles. If the sphere is in the way, we can always turn off the body and it just leaves us with these two circles. Whoops, not the actual plane itself, but the two circles. There we go. And we would like to extrude these out 5 millimeters and then turn our bodies back on and say, no, we don't want to cut them. We actually want them to join. So the sphere and the two wires coming off are one entire component. And then click OK. And then again, for our physical material, we want this to be glass. We don't need ceramic, we would like glass right here. And the most similarly visually similar would be this cast gray color. So let's go ahead and drag this on there and click close. And as you can see, it is glass, so it is slightly transparent. That looks great. All right, and then that will be the end of that component. So we go ahead and activate the top file and then save this. Our next component is going to be something known as a heat break. So a heat break is essentially just the in-betweeny part, that's the technical term, between our heating block, which is this large aluminum prism that we have here, and the heat sink. So as a very fundamental truth in 3D printing, yeah, we want a lot of heat to melt our plastic, but as soon as it's done, we need to get that heat out of there as fast as possible because we don't want to form heat creep, where now the thermal energy is now working its way up everything and starting to melt plastic higher up than it really should do. This can cause clogs, this will degrade all of the PTFE tube very, very quickly. And so we want to be able to get rid of as much heat as possible. Yes, we do have a fan that's actually blowing over our heatsink to disperse as much heat as possible, but we want to limit the amount of heat traveling upwards. And that's where the heat break comes in place. It is a very, very thin cylinder with a threaded end, so we can actually screw it into our heat block, but it's also made of very, very thin walled steel, so it's preventing heat from traveling upwards, hence the name of break. This is also a very, very common part where people are trying to replace their nozzle and they don't grab onto the heat break or the heat block with a pair of pliers, and they just wrench the nozzle off, and this cracks the heat break very, very quickly. And then you go, oh no, now I have to buy an entirely new hot end assembly, and that's just a pain that we don't want to deal with. So anytime you're replacing a nozzle, please grab a pair of pliers and grab onto your heater block. Going back to the CAD, we are going to be making a new component, and we can be making a new sketch on the front plane. And most importantly, we are actually going to be turning off our heater block and any of the other components that kind of get in the way. We are going to hit P for project, and we are going to be working off of the very top of the nozzle because our heat break should be screwed all the way down to touch the very top of our nozzle. And then we can make a sketch that builds off of this. So using our line tool, we are going to be making a slightly strange shape here. This is going to be a component that has got a lot of random parts to it, but as you'll see, will make sense a little bit further on. For example, this is going to be the inner hole of our piece. The thickness that we have for our component will be the distance between there. This face will end up being the threaded section, and this top angle will then be fitting into our heat sink. So first things first, let's put in some constraints. So that angled line that I made there, that ain't supposed to be angled, so we're going to add a horizontal constraint, and we're also going to add a collinear connection between the very bottom of this and that projected line that we had. There we go. And we can now go ahead and go into our packet so we can grab all of our dimensions. What you'll notice is that this is a very tall, skinny part. All right, so this component is all dimensioned out. The really funky things that you guys may be a little tripped up on, this angled line is set to a 30 degrees angle, And we also have another parallel 30 degrees line right here, but everything else should be pretty normal. So let's go ahead and finish this sketch, and this is going to be a revolved profile about that blue Z-axis. There we go. And we can just hit OK, and then this top threaded section is going to receive a very similar thread down below. This is an M6, and then we can keep this as OK. Now this component is still made out of steel, and the default material for any Fusion 360 part is always steel. So we can just say this component is totally done, so we can go ahead and activate our top component. Now our next component is going to be another part that builds on top of the heat break. This is going to be our heat sink. Now a heat sink is basically the opposite of a heat source. Instead of producing heat, we're trying to get rid of it as fast as possible. If you've ever built your own computer, the word heat sink will sound very familiar. That is the component that would go over any components in your computer that produce a lot of heat, where you're trying to get rid of it as fast as possible. Most often they're made of aluminium because it has a very fantastic heat conductivity setting. And so any heat that you put in, it's going to be translated out very quickly. So if we have a lot of surface area built into this component and we put a fan in front of it, we can wick away a lot of heat very easily. Again, we are going to be building it on top of there, so we can just make a new component that is internal. Like I said, this is going to be called a heat sink. And we can make a brand new sketch on the front plane, and we can project the very top of this component. Now this sketch is going to be a little bit complicated because we are going to be making half the sketch now, then making a linear pattern to make the rest of the ribs that we can dispel with a lot of the heat. So we're going to be starting off by making a little snake pattern down here, where it goes back and forth until it's traveling upwards over to the left, where we can put in a little 3-point arc. Doesn't really matter what it looks like. And then up and over and down again. So just like always, we want to be putting down all of our sketches, then adding any constraints. For example, this should not be an angled line, that should be nice and vertical. This point and that line should be directly over one another. Similar thing with this point and that flat section. Let's move that over, there we are. So everything should look a little bit closer. Then we can add in all of our dimensions. Another thing that will be a heck of a lot easier is I'm going to be adding a construction line right through the middle. This will be our axis of revolution, so we don't have to click the blue Z-axis as our axis of revolution, because it will be a little bit harder to get access to as we build up more and more parts above it. So let's go ahead and add in all of our dimensions for this part. So now that all of our dimensions are put in place for this, we do have this little kind of straggler over here, and we're going to be adding a set of 9 linear patterns of this section right here going upwards. This may be a little bit complicated as we add more and more lines to this, so just kind of move around all of your dimensions lines so you don't accidentally get them mistaken for any of our sketch lines we have in there. So let's go into create and add a rectangular pattern. The objects that we would like to pattern would be these 4 lines right here. We would like to add 9 of them going vertically. We don't care about any of them left or right, so where it says quantity 3, we can just reduce that down to 1. The distance type, we would like to change this to spacing. As we can see, this line right here is 0.8 millimeters. That gap right there is 1, which means our distance should be negative 1.8. So now all of these lines now add up and they stack very, very neatly. And we can just click OK. And then this last point, that will then line up with this point right there, just to bridge the gap with a coincident. So you can see just how thin all of the profile is, especially up there at the top. this is meant to translate heat not upwards but away. So as little surface area as you can get as possible, the better. So we're going to give this another rotation. We're going to be revolving about that really handy construction line we made there. Perfectly normal revolution. We can click OK. And then this, for some reason, is always anodized this really lovely red color. So we can go into appearance. We can look up anodized. There we go. And it's usually always this nice glossy red. It always looks kind of neat. Now this is a rotational drum heatsink, I guess you could call it. But usually all of them will have flat front and back, so it can be screwed into a mechanism and still be kind of a low profile. So we're going to be cutting off this front and back section. Let's go ahead and make a new sketch on this top plane, and we're going to be adding a little rectangle. And we want this to be symmetric about either side. So we're going to be adding a point to this top horizontal bar. There we go. Anytime you see that little triangle, that means it's always going to be in the middle. And we can make that point and the origin horizontally constrained to each other. So now if we move the width, it'll now be nice and symmetric. So our rectangle is going to be 18 millimeters by 5 millimeters, and the very underside to the origin is going to be 6 millimeters. There we go. Technically that 18 millimeters just doesn't really matter as long as it extends past this circle. If we really wanted to, we could completely get rid of that and then add a coincident relationship between that bottom point and that circle. That would also work, either one you'd like. But regardless, we are going to be finishing this sketch, and we are going to be extruding that profile all the way through our entire piece. We're going to be cutting it all the way down. Again, you can always change your extent type to object and then select this bottom face, so it will just cut up to that surface, and then we can click OK. And we only have one flat side, so we may as well mirror that feature. So we're going to click our mirror tool. What features would you like to mirror? Well, that's going to be that extrusion cut we just did. And then that mirror plane, well, that's going to be about the front plane. That's how we're building everything off of each other. There we can just click OK. And now we have something a little bit more realistic. This hole at the top, this is going to end up being an M10 thread. So before we do that, we may as well add a little light chamfer to there, something like 0.5 millimeter. That's great. And then let's add a thread. This is going to automatically adjust to be an M10, and we always want that to be modeled thread. So to join this piece to the rest of our 3D printer, we actually need to put 2 holes on either side that we can pass some bolts through to join this to our X-axis frame. So we're going to make a new sketch on that front face of our piece, and we're going to be making 2 circles. These are going to be exactly the same size. These will be 3 millimeter in diameter. Let's bring it back up. There we go. These also want to be perfectly flat, so we can just add a horizontal constraint to them. And these are going to be 4 millimeters from the top, and these want to be 14 millimeters in spacing. They actually extend a little bit further past this flat section, but as you can see, they aren't very symmetric. So what we can do is add in a bit of symmetry. There is a symmetry constraint, but it needs to be symmetric about what? So let's make a construction line. It doesn't need to be very big, but now we can say, well, what do you want to make symmetric? I would like these 2 points about this line. You have to do it in that order or else it won't work. Then we can say finish sketch, and we would like to extrude both of the circles. Don't forget there's this little bit that kind of hangs out. And we want to cut these all the way through. So I'm going to change my extent type to the object and then click that back face. There we go. So just like the heater block, we also need to put in a little grub screw on the very bottom. So let's add a new sketch on this back side. This is going to be a M3 thread. So of course we're going to be adding a 3 millimeter diameter circle. Let's bring that back. This can be horizontally constrained with the origin, and then we want the center to the bottom to be about 2 millimeters. Not bad. Then we can extrude cut this all the way through this piece. Again, we don't want it to go all the way through on accident, so we can just say to the object, to that ring, and that'll perfectly map to the inside of that curve. We can add a little bit of a chamfer to that, something small, whatever you'd like. Something like 0.25 millimeters would work nicely. And then we can add a nice little M3 thread. And all of these threads that we put in there, we are going to be importing some hardware so we can bolt everything together. Now, if you remember, on the heater block, we actually made two holes that go right the way through them, that we can pass some countersink bolts all the way through them and then screw it into the heater block. Where are those holes? I don't really know, but we can use the power of project to actually select those holes and then project them onto the surface. So let's go ahead and make a sketch on the very bottom of our heater block, and then we're going to be projecting these two holes. So we can select that one right there and that one right there. I only really care about giving me the very center of these holes, and then we can click OK. And then we can turn off the heater block as well. So now we can finish this sketch and then extrude those two circles all the way through our piece, but not all the way. We want to finish it at that top rib. So again, change your extent type to the object and click the underside of that top rib. So that way it'll cut through all of these, but it won't touch this top surface. Because remember, we still have these bolts that go through. We don't want to have two interfering bolts that pass through each other. And then we need those bolts to be screwed into something, so we can just add some M3 threads to both of those holes. Check modeled. If you're ever selecting multiple threads, you just want to hold down Control and then select all of them. And then we can just click OK. So now this component is all done and dusted. Now we can go ahead and activate that top bar. Just in case you forgot, always double check your timeline may be getting a little bit out of whack. So you want to make sure you do make some groups for all of your components. Remember, select the first one, hold down Shift, click the last one, right click it, and then create a group. There we go. And then if you want to check your progress, we've actually made a fair few components. All the way through, we've got our heat sink, our heat break, our heater block, our nozzle, our thermistor right there. Oops, and we forgot the thermistor right there. And then our heating element right there as well. So far as the all the hardware that can be passing through, we'll be having two big bolts that will go through. We're going to be having two grub screws, or two set screws, that hold the heat block to the heat sink. And then we're also going to be having a small little bolt that holds the thermistor in place. And then two large bolts that pass through the heat sink into the rest of our printer. So with our top component activated, we can now make a new component. This one is going to be called Bowden Connector. This is a really strange little screw that's got all these plastic teeth in there, a little plunger mechanism, and it's what holds our PTFE tube to the rest of our mechanism. Remember, always make sure that this is an internal component for this project, and we can just click OK. And we'll start off by making a little cylinder that will eventually end up being a threaded cylinder. So we can go into Create, add a cylinder. We can make it on this top surface, and this is going to be a 10 millimeter in diameter by -6 millimeters going downwards. So it does interface with the threads. Unlike other components, this won't cut out anything else because we are selecting this to be a brand new body. So it exists in the same area as the thread from the heatsink, but it doesn't interact with anything else. Then we can go ahead and add a mating M10 thread to that surface. Yes, we would like it to be modeled. And then we can make the rest of the geometry building off of that surface. So let's make a new sketch on that top plane. If you find that as you build more and more components, it gets harder and harder to see, don't forget, you can just turn them off in the browser. Things do get complicated and they don't need to be, so just turn them off. We can go back into the Create, into our polygon section, and we can make a 10 millimeter hexagon. So the distance from the top to the bottom will be 10 millimeters. Again, you don't have to, but it's maybe a little bit easier if you select the top plane to be horizontally constrained. And then we can finish that sketch. So we're going to be extruding up both of these profiles 5.5 millimeters upwards. And then we want to have a hole that goes right the way through it. We could have made this in a revoluted sketch, but often it's just easier to just build it as individual planks that get joined together and then cut holes through it. So to do this easily, we are going to be making a hole, so type H on your keyboard, select this top surface, and this is just going to be a perfectly normal hole, 4.25 millimeters in diameter, and we can drag this blue dot right to the center. We don't need this to be threaded, so we can just make this a simple hole. Like I said, we want to make the diameter 4.25 millimeters, and as far as the depth, we can just have this extend all the way through. It doesn't really matter, as you can actually click this arrow to bring it all the way down, as long as it's cutting through our piece, and we can click OK. So to construct the very top section, we're going to be making a new sketch on that front plane, and we're going to be projecting this top surface here. The actual plunger mechanism is tremendously complicated, and so for this class, we're just going to be making it as one solid piece. So go ahead and add a 3-point arc somewhere in the middle. Doesn't really matter. But as you can see, this one is actually, well, accidentally snapped to the midpoint of this line. You can see there's a little triangular midpoint symbol on there. I don't want that, so you can click it and hit delete. Now I can move this at any which point I would like. So now we can add in the rest of our geometry just by going to the line tool. We're very, very simply going to be going up, around and over, and then coming back down. And we do want a little bit of gap in between this left vertical line and our green or our blue z-axis right there, because this is going to be a hole. You may find that it's a lot easier if you look at a cut view of this. So if we actually go into our sketch palette, you'll see there's a little area called slice that you can check, and it gives you kind of a bifurcated preview in an identical way to our section analysis in our inspect area. But this just makes life a little bit easier to work with. So we can always kind of click and move this around, so it's very easy to see where it is cut and where it hasn't. We can also put in a very simple construction line for any of our radial dimensions that we're working with. So the last thing to do is add a coincident relationship between the center of the arc and that projected line we made. And that is looking good. Then we can just go ahead and finish sketch and then revolve this profile about that central axis. Then we can click OK, double check the operation is set to join and not new body. And then finally, because the lower section of this part is made out of steel, but the top section is made of plastic, we want to kind of give that feel a little bit. We don't want to make the entire thing steel or the entire thing plastic, but we can alter individual faces. So you can click A for appearance, and then we're going to look up a really common plastic called ABS. And if you go up to the very top, instead of having bodies / components selected, we're going to go to faces. And then we can very simply click and drag this onto all the pieces or all the faces of this component that are in fact plastic. That is this little shank right there, and then all of the faces of this little top plunger mechanism that we have up top. All right, that looks good. Then we can go ahead and activate our top component, and we can see how everything else is looking. So our very last component that we're going to be making is called the PTFE tube. PTFE is just a very low friction plastic. The corporate name is Teflon, so it's a very, very slippery material, and when we pass our filament material through it, it doesn't incur a lot of friction, so it's really easy to push it through, and you don't wear out your extrusion motor too quickly. This is actually going to be starting, or if we do a little section analysis, you can see that the very end of our PTFE tube has to go all the way through our Bowden connector, through this little section of the heatsink. It's going to be mating with the heat break pretty closely, and then it's going to stop right at the very top of our nozzle. If there's even a little bit of gap in between the top of the nozzle and the underside of our PTFE tube, then this is an area where melted plastic can kind of get trapped, and then it will heat up, cool down, heat up, cool down, and it starts to break down from a polymer down to a monomer, which is this really gunky, almost tar-like plastic that just never re-solidifies. As far as maintenance goes, it turns into a nightmare glob mess. So we want to make sure that anytime you have a PTFE tube, it is pushed down all the way onto the top of our nozzle. So we'll be making a little, well, almost two coincident circles to act as our tube, and then we're going to be making a little path for it to go all the way up and out because this is a curved bit of plastic. So just to enable this, we're going to be making a new component. This one is going to be called PTFE tube. So we'll be making a new sketch on the very, very top of our nozzle, which is a little hard to see right now. So let's turn off the rest of our components. There we go. And we can select that top surface, and we want to be making two coincident circles. The outer one is going to be 4 millimeters. The inner one is going to be 2 millimeters. That's great. We can hit finish sketch. If you go, this analysis is kind of in the way. It's kind of distracting me. The analysis is going to be found inside its own tab, so we can just turn that off. No biggie. Then we can make a new sketch on the front plane, and this is just going to be the path that the tube will follow. So we can just make a, let's say, an 80 millimeter line going straight up, and then an arc that kind of goes off to the side. And this arc can be whatever you'd like. I'm going to put it as a 60 millimeter radius, and where these two ends are actually tangentially connected. I do want to make sure that the end point matches up with the center of our circle, so we can just use the coincident tool for that. And then we really don't care too much about the length of this. It can be whatever you'd like. But anytime you have some aspect of sketches that can change, you may as well use the fit or the fix tool to kind of lock it in place so all of your sketches are defined. And then we can just hit finish sketch. So we have a path for it to follow. We have a little profile. This means we are going to be using a sweeping tool. So let's turn off the nozzle, go into create, hit sweep. What is your profile? Well, that's going to be this little circle here and a little ring on the inside. Our path is going to be this straight line, and the arc, you can see we do have that tube going all the way through. Great. And then we can hit OK. Going back into the physical material, we actually do have the ability to put in PTFE. So if you go into plastic, if we scroll right the way down, we can see PTFE is right there. So we'll click and drag that on the component. And usually PTFE is always a really lovely royal blue. So let's double click that PTFE, go into advanced, and then we can mess around with the appearance. So the RGB, we can change this however which way we'd like. That's a nice color, kind of liking that. We can hit apply, and then get rid of that, get rid of the physical material, and now that's looking pretty accurate. Great, so we have now completed making every single component that we're going to be working on. So I'm going to be turning back on all the components and then reactivating that top piece. That looks great. But as I'm sure you're all worried about, all these components can move. Big, big, big issue. Let me just undo all of that. So if we wanted to, because all of our pieces are in the right location, we could go individually and add an as-built joint to every single component, back and forth, back and forth, back and forth. That's going to take a while. Engineers are lazy, so let's add in what's called a rigid group. So under the assemble menu, rigid group is an even more simplified version of joints, where it's saying click as many components that you'd like, and as soon as you click OK, it just rigidly holds them in place. So instead of clicking all these components, I'm actually going to go into my browser, select the nozzle, which was our first one we made, hold down Shift, click the bottom, PTFE tube, say, yep, do you want some rigid constraints? Yes, I do. And then we can hit OK. And now because our nozzle is fully grounded and the rest of them now have joints that connect them all together, everything else is locked in place. Perfect. Now we can go and add in all of our screws that we need. So now with all of our made components done, we can now add in all of our hardware, and we're going to be starting off with some of the grub screws. So just like before, we're going to be adding in a McMaster car component. This one is going to be for the M3 by 4mm grub screw. Remember, you always want to download this as a 3D step file. A step file is just a very, very similar 3D file to an STL, the kinds that we use in 3D printing, funnily enough. So we can just pull this out. We can be starting off by putting this in the underside first. So if you want to, we can rotate this so it's about in the right orientation. And then we're going to type J for joint, and we're going to select, well, somewhere on this, the outer ring, so it puts the joint origin right in the dead center of that circle. Then we can move over to a similar place and type and select the outer ring of the circle, so that, there we go, so it slides in perfectly. This is actually set to slider from our last fire piston project, so I'm going to change this over to rigid. There we go, kind of shakes, which means it is fully cemented in place. That's perfect. So we can just click OK. But we do need another one. So instead of going through the whole process of downloading a new step file, why don't we just copy and paste this? And that's exactly what we're going to do. We are going to be selecting that grub screw, right-clicking it, copy, and then right-clicking again and saying paste. And then we can move this up and out of the way, and then click OK. And now we have the exact same grub screw that we can use for that other location. So similar process, we're going to be adding a joint. You can actually click either one you'd like first. So if I wanted to, I could click the ring of the chamfer here, and I could click the ring of the grub screw. Doesn't make a difference. I know this looks totally completely wrong, but as soon as I click OK, you'll see it'll flick back into the correct location. Perfect. Moving onwards, we are going to be adding some more components. So we are going to now be typing in this code for the the flathead countersink bolts that are going to be joining the heat block to the heat sink. These are the M3 by 20. Again, we want to download it. It's going to be popping it right into the origin, which is always a little bit tricky to see what's going on. So we're going to be clicking and moving it out of the way. So it's at the origin, but it's upside down, so we can always rotate this 180 degrees, clicking OK, hitting J for joint. I'm going to be selecting this top section of the ring, moving over, top edge of that top ring, moves everything in place, clicking OK, and you can see it's now passing through, through the entire heater block, and then just barely screwing into that threaded section, and it has a lot of clearance through all of that. And just like our other piece, we are going to be copy and pasting this, again, just over to it. If you remember the distance between the two holes, I certainly don't, you can move it over that amount and then add an as-built joint. That may be just as easy, but we're going to be adding in a joint, again, top edge, top edge. Great. We've got a random one-off screw right here. The screw that we have is a very strange, kind of stubby Phillips head bolt. It's again another M3 thread, but this is a really funky one because it's not being held in super duper tight. It is going to be there just to hold that glass bead, a little thermistor in place, and if we tighten it too tight, that'll actually interfere with the resistance of the wires that go into it. So if you really over tighten it, it'll give you a big error saying thermal overload or thermal runaway, saying there's too much heat going on, I can't get any information back, I don't know what's going on, big errors. So this is just lightly tightened in, just so it kind of holds things in place. So you can click OK after putting in the right orientation. Again, adding a joint, but this one we're going to add, or we're going to select this underside of the ring. Select the outer ring there. There we go, and it joints it in just fine. If you wanted to go the extra step and kind of give some information to another person that would see this sketch, you could pull this bolt out just a little bit, just to signify this isn't screwed in all the way. Then we can just click OK. And then as the last two components, again, we're going to be putting in some more bolts. This is going to be an M3 by 16 bolt. And this is going to pass through those 2 holes in the heatsink and then join it to the rest of the frame. So we can pull this bolt out of the way, add a joint, select that ring on the front of there, go to the underside of my bolt, select the bottom ring of the head, and you'll go, yep, that's in the right orientation. Click OK, and you can see it passes through the front of it and then into the back. We do need to make another one for the other side, so select that component, Control C, Control V, move it over, click OK, and then add a final joint, again, to the front side of that ring, flick it around, underside of the bolt head, and hit OK. And there we go. There we are, guys. This is now a perfectly done Ender-3 Hotend assembly. Hope you guys learned a lot about 3D printing. Now go ahead and 3D print something really cool and have some fun.